Today we are learning about Friedel-Crafts chemistry. Yep, today we're going to be learning about the last couple of reactions in electrophilic aromatic substitution. And so here we're going to review a little bit about the general mechanism of EAS reactions. First, we have the formation of our electrophile. Then we attack our electrophile with our aromatic ring. This is going to form our rhenium cation that we talked a lot about. And the stability of this is dependent upon the substituents on that aromatic ring. Then we're going to have a restoration of the aromaticity. And a little review about this. Remember that when we have an aromatic ring that has a substituent on it, let's say, for example, we'll take this carbonyl. When we do an EAS reaction, we have some kind of an electrophile. The substituent on the aromatic ring dictates where the electrophile is added. So in this case, this carbonyl is an electron withdrawing group. This would direct this meta, or as we've talked about before, it's meta allowing. It allows the chemistry to go on the meta position. And so here, we will have our electrophile added in the meta position. There are two types of Friedel-Crafts chemistry we're going to learn about in this video. So you have Friedel-Crafts alkylation. So essentially you have this alkyl halide. Typically we use an alkyl chloride. They're very inexpensive and readily available. And what we're going to be doing is in the reaction, we're going to be essentially forming this R+. Okay, this is going to be our electrophile. We also will talk about Friedel-Crafts acylation. And in this case, our electrophile is going to be what we call an acylium ion. And we'll talk more about how we can make these in situ. Let's take this example here where we have benzene and ethyl chloride in the presence of aluminum chloride. Our first step of EAS reactions, again, is formation of our electrophile. So let's go ahead and do that. What we're going to do is the lone pairs on the chlorine are going to add to our Lewis acid, our aluminum chloride. Making the aluminum negative, it's now bound to the chloride. And then this is bound to our ethyl group. In this case, you could look at this and think about this chlorine bound to this aluminum trichloride being a leaving group. So nominally, you could think about maybe drawing an arrow here and forming this carbocation. But we know that this is unstable. So in this case, if you form a primary carbocation, you won't draw this cleavage of the chlorine carbon bond. So in this case, instead of drawing this, we're going to use our complex here that is still bound to our Lewis acid. So this will be our active electrophile in this case. We will go through an example where you'll get a more stable carbocation in this video. All right, we formed our electrophile. The next step is we're going to add our aromatic ring. Here we've got benzene. So we're going to attack this electrophile here at this carbon with this awesome leaving group. We now have our rhenium cation. We also still have our complex. Next, what we're going to do is, that's right, restore the aromaticity. In this case, we're going to use the electrons between this chloride aluminum bond. So we'll draw our arrow starting here. We're going to pick up this proton, and then we're going to restore the aromaticity. This is going to lead us to our alkylated product. we form our aluminum chloride back, aluminum trichloride, and we also form some HCl. And there you have it. This is step number 3, and that is the mechanism for this Friedel-Crafts alkylation. Now, one of the problems with Friedel-Crafts alkylation is that you can imagine that the product we're getting, we know that this is activating, right? So this group is an activator. So when you think about this chemistry, you're introducing a group that is activating the aromatic ring more than the starting material. So if you were to compare our starting material and our product, you would say that the product is actually even more reactive than our starting benzene. In this case, many times what we'll see is that the reaction continues as soon as we make ethylbenzene, our product. If ethylbenzene sees that electrophile, that ethyl electrophile that we formed, it will react with it. And so what will happen is that you will end up finding that you will have products where this will add again. So here we have another ethyl group, and this could react yet again, because now this is even more reactive. And so on and so on. So one way that we circumvent this issue is that typically what you'll see is that we will use excess of our starting material, as long as it's something that's fairly inexpensive. Benzene is not an expensive starting material, so we would use excess benzene so that as soon as we make our electrophile, the majority of the aromatic rings it sees is in fact benzene. So this is one way we can get around that. A second thing that you'll find with Friedel-Crafts alkylation is what we briefly touched upon. When we form this electrophile, you can have rearrangements where you form a more stable carbocation. So let's dive in. In the first step of this reaction, we have N-butyl chloride. What we're going to do here is we're going to react this with our aluminum trichloride. One of the lone pairs from the chlorine is going to attach to our Lewis acid. Now, what can happen here is that one of our hydrogens on the adjacent carbon, it can do a 1,2 hydride shift. And we've seen this before in Chem 343, where we will make the most stable carbocation. The way we're going to depict this is we're going to start our electrons and our arrow between the carbon-hydrogen bond. That's where the electrons are coming from here. And then we're going to push it over to the carbon adjacent to it. This essentially then kicks out our leaving group. And what we have now is a secondary carbocation, which is more stable. In this case, these Friedel-Crafts alkylations can form these rearranged products very simply. And so what will happen is this is now our electrophile that benzene will see. So in our second step, we will have benzene and we will react it with this electrophile that we've formed. And again, we need to restore then the aromaticity in step 3 by taking the electrons from our chlorine aluminum bond, and then we'll push these down to form our new double bond. So not only can we get these rearrangement products because this is nominally making this carbocation, especially if it can shift and do a 1,2 hydride shift. So Friedel-Crafts alkylation not only does this rearrangement, but as you can see, remember that our product here is even more active than our starting material, which again can lead to this overalkylation. An alternative to the Friedel-Crafts alkylation is to also use different electrophiles where we're still forming this type of carbocation. In this case, we're using again some chemistry that we've learned before, where we have an alkene in the presence of an acid. The same rules apply for EAS chemistry here. The first step, we're going to make our electrophile. Here we have our alkene. And then we have our strong acid, our H2SO4. We're going to protonate our alkene. Remember that the proton is going to go on the least substituted carbon, and our carbocation will then be on, in this case, a tertiary carbon. This is our electrophile. Now we're going to react it with our aromatic ring. Here we've added our tert-butyl group. We have our rhenium cation. Now we're going to use the conjugate base of our strong acid here to deprotonate this proton and reform the aromatic ring for our third step. And now we have our product. Again, this is an alternative to Friedel-Crafts alkylation, where instead of using an alkyl halide, we're going to be using an alkene. Essentially anything that we can use that would make that carbocation in situ could react in a Friedel-Crafts type mechanism. Now, one way to get around the limitations of the Friedel-Crafts alkylation, where we have overalkylations and these rearrangements, is to use what we call Friedel-Crafts acylation. Now, you might think to yourself, now wait a second, we were adding alkyl groups to our benzene ring. This has a ketone on it. We're going to learn a really cool reaction to get rid of our ketone here. But what I first want to do is walk through the mechanism of this, and then we'll talk about how we can actually change it into just an alkyl group, which would be the product we would get from Friedel-Crafts alkylation. One thing you'll notice is that you need an acid chloride. And you still need a Lewis acid here, which is aluminum trichloride that we'll use. Again, the first step for EAS reactions is to make our electrophile. That is right. So here we have our acid chloride. We're going to add aluminum trichloride. One of the lone pairs from the chlorine will interact with this Lewis acid. Now, what will happen next is very cool. We are actually going to use one of the lone pairs from our oxygen, and we're going to push it down to form something that looks kind of wonky. I'm not going to lie. This may look kind of weird at first. And here we're going to kick out our really great leaving group. Now, what just happened with those arrows? You'll see that we made a new oxygen-carbon bond. When you have this double bond here, the structure is no longer bent like we've shown before. It is now linear. We have our methyl group. Our oxygen has lost electrons. It still has one lone pair. And this is what we call an acylium ion. We still have our aluminum tetrachloride. The second step is the same thing that we've seen before. The only difference, again, is that we have a different electrophile. For Friedel-Crafts acylation, we still have our aromatic ring, and in this case, we're going to use this acylium ion as our electrophile. Notice that I attack the carbon. I'm attacking this carbon that's triply bound to that oxygen. I'm going to push these electrons up now. What does that form? It forms our rhenium cation. I made a new bond with a carbon here, and that carbon is still doubly bound to that oxygen. That carbon still has that methyl group attached to it. Now we're going to do the third step that we've seen before. We are going to restore the aromaticity. We're going to take the proton from here. The electrons from that carbon-hydrogen bond will push down and restore the aromaticity of this aromatic ring. Now, on an exam, you wouldn't have to label these. I'm essentially calling them 1, 2, 3 to help you remember these steps in these reactions. Again, one thing you'll notice with Friedel-Crafts acylation is that you make this acylium ion, which is very different than the other EAS reactions that we have learned. Now, before I said that this could be something that could be used in place of our Friedel-Crafts alkylation. One thing you'll notice is that there's no room for rearrangements here. Because we have the carbonyl, when you look at the arrows here in blue, you'll see that there's no room for these rearrangements. This acylium ion helps us keep this alkyl chain intact without forming any rearrangement products here. Now, one way that you can then take our Friedel-Crafts acylation product with the ketone and you can turn it into this alkylated benzene ring is by using what we call the Clemmensen reduction. We won't be going over the mechanism of this. Here, what you'll see is we use a zinc-mercury amalgam. It's kind of an older term of when you have this mixture of metals that we use. In the presence of HCl, you will remove the oxygen of this carbonyl here. This is a great way to use our Friedel-Crafts acylation, especially if we were to have, say, an additional carbon group here. Forming this product via Friedel-Crafts alkylation would not be possible because we would get a rearrangement product. So by using Friedel-Crafts acylation followed by a Clemmensen reduction, we can circumvent the problems of Friedel-Crafts alkylation of the rearrangements and still form those alkylated products. Now, another thing that you will find is that the product here is actually less reactive than our starting material, our starting benzene. So it's less reactive to EAS. Now, why is this useful? Remember with Friedel-Crafts alkylation, over-alkylation could occur because our product was more active. This product is less active. It's got this carbonyl on it, pulling electron density away from our ring. So in this case, Friedel-Crafts acylation not only, one, eliminates this over-alkylation problem. Two, it also can be used to circumvent the rearrangements that can occur in Friedel-Crafts alkylation. Now, both reactions are very important, and they both have their utility in different situations. I do want to highlight a limitation with Friedel-Crafts acylation. Because we are using, in particular, the acylium ion as an electrophile, we typically need an aromatic ring that is near the nucleophilicity of benzene. You can get away with some electron withdrawing groups. However, if you get something that is too electron withdrawing, typically the sulfonic acids, a cyano group, or a nitro group, these groups will not react in Friedel-Crafts acylation reactions. Okay. One thing that's interesting to note is that in these reactions, nitrobenzene is commonly employed as a solvent. And so this tells you right there that if this is used as a solvent for many Friedel-Crafts acylation reactions, and this is interesting because we know that nitrobenzene is too deactivated to react in Friedel-Crafts acylation reactions. So again, it's commonly used as a solvent in these. So just remember that for Friedel-Crafts acylation, although it does solve a lot of the issues we found with alkylations, it requires a more activated arene. The rules of which I would like for you to remember that if any of these three are bound to the aromatic ring, this Friedel-Crafts acylation will proceed very slowly. There's one last concept I'd like to go over for this section of this video. We've discussed how the stability of benzene is very unique and it's much more stable because of its aromatic nature. Here we're going to look at a hydrogenation reaction. Typically, under mild conditions, for example, 1 atmosphere of hydrogen and maybe room temperature with this palladium on carbon catalyst, we will see hydrogenation of our alkene, but the benzene, this aromatic ring, is not touched. The heat of enthalpy for the hydrogenation of benzene is much, much higher. In this case, we would need to really push the reaction. We would need to use harsh reaction conditions. Here I'm showing very high pressures of hydrogen. We're going to be using a nickel catalyst. We have to heat this reaction to a very high temperature. And here we'll see the hydrogenation of both the alkene and our aromatic ring. The alkene still has a lower enthalpy of hydrogenation. Our aromatic ring still has a much higher enthalpy of hydrogenation. However, these harsh reaction conditions can push the hydrogenation reaction to where we get hydrogenation of everything. So these are two additional reactions that I wanted to share with you that round out our discussion of reactions with benzene.